number 16. First of all, let me introduce our team. Is Jose Arraut, Alejandro Infante, Jorge Larrarte, and Evis Reyes. Today we're going to give a presentation about the NASA Lunabotics. Basically, Lunabotics is a competition, the NASA competition for university students around the world. This competition takes place at the Kennedy Space Center in Florida. The challenge of the students that participate in this competition is to design and build an excavator. This excavator will be able to mine and deposit a minimum of 10 kilograms of lunar simulant in 10 minutes. And also the objective of this competition is to improve and find solutions which can be applied to future excavator devices. This is the problem overview of our project. Basically, it's the same as I said before. As you can see at the bottom of this picture, this is the platform where the competition takes place. Basically, the excavator starts from point A to point B. It travels from point A to point B. In point B, they collect the lunar simulant, travel back to the collector when they deposit the lunar simulant. Now, Jose is going to explain more about the project.
Here we have the robot design. As you can see, all of the things has to be to make sure to follow some of the regulations made by the NASA. The first thing is to go ahead and be sure to have the maximum dimensions, that they will be from 1.5 to 0.75 meters wide times length. Then we have the material that is going to be the sheet metal and aluminum. Also, they have to check for the durability, the weight. Also, another important thing that they need to reduce or minimize the power consumption. And when they are doing the task of picking up all the dust, they have to minimize the dust creation. Another very important thing is to reduce or to increase the traction during the sample. As you can see here, we have some of the examples used by previous universities. Here we have the case of the track caterpillar system. Now we have the blade that is like a singular cylindrical wheel with a bunch of blades around it, so it would improve the traction during the pull. Also, we have the regular wheels. For the pickup system, we have the regular buckets, and then we have like a lingo buckets together, like a small, working in a vertical plane. Right here we have the final designs for the competition last year. We have the one made by the University of South Dakota at the left. That was the one that worked in a vertical plane. Then we have the caterpillar type that was made by the West Virginia University. And here we have the winner that was made by the Aeronautical University in Arizona. Now Jorge is going to explain how that system works.
Our conceptual design was taken from the champion of the Lunabotics competition. As you can see here, the end effector is rotating. As it is rotating, it is collecting all the data, all the material, or all the sample. In this case, it's the same because of the practice because of the session practice. Here, the robot joints leave the material, and then the robot, because of the wheels, follow a forward position into a specific place. When in here, it is disposing all the rest of all the material recollected, and in this position is the second task of the robot, that is disposing all the material. Now, Alex is going to talk about the future concepts.
So, in the future, we should be expecting robots to have more human-like characteristics, being that as nowadays robots are very limited to the amount of movements that they can make to complete certain tasks. Your hand, it's very complicated. You know, you look at it, it's pretty simple on the outside, but inside it's probably even more complicated than the most advanced computer that we have right now. It has over 22 degrees of freedom, which is nothing close to what robots have, which is around maybe 5 or 6 degrees of freedom at most, which, you know, degrees of freedom make simple tasks like picking up a glass, you know, especially easy compared to robots that can make a task as simple as that, as, you know, as complicated as, you know, building a nuclear bomb. You know, it's just that much more complicated with less degrees of freedom. So in the future, you guys will be expecting more human-like characteristics in robots, starting with hands. You know, hands are going to be, you know, the forefront of the technology, but you will be later on seeing maybe feet, maybe robots walking around just like humans. So expect that. Expect human-like characteristics in robots in the future. Thank you.
Now let's go to talk about the product calculations. In here, we follow the Lunabotics principle, but we were using a 3-revolute robot arm. This because it was as we learned in class, we follow the same procedure. We define a path. In this case, we designed an electrical path because we were trained with a parabolic path, but it was really giving a not a physical solution. Alex is going to talk more about that and go ahead. But in here, once we define the path using the equation of the ellipse, we obtain the coordinates in x and y positions. Then with those, we calculate the final angle or the angle of the n effector, and after that we did perform all the calculations to obtain the angles of each link respect to the x-axis. In this one, the horizontal axis. This all was done in order to model all our robot in SolidWorks. As you can see here is the elliptical path that I was talking about. We define the first point as a 0 in y and 1.5 in x. We follow the calculation of the ellipse equation, and when it reaches the 90 degrees, or when it's completely vertical, the end effect of the end effector is in the vertical and the completed vertical position. We try to make it more challenging because we want to obtain a better disposal of the material. And so that reason we create a linear path in there. In here, we can see the kinematic and the first kinematic animation of the video in SolidWorks. You can see the end effector is moving the elliptical way, but we were trying to try an error, and we were trying to move as our criteria the end effector angle. Now Evis is going to talk about the final design and the material selected.
This is our final design. Basically, this is the assembly of the all part that we did in SolidWorks. Basically, is the tire, the frame, the body, the link, and the bucket. For the material, we selected 2 types of material. We selected the aluminum 1060 for the frame and the body, and for the link and bucket, we selected the steel. And this picture also show you the final polish of our final design. Now Jose is going to explain more about our project.
Okay. Well, here we have our design actually working. As you can see, here we have the movement of the Lunabotic that is following the path, the elliptical path, and it's go all the way up until it reaches the 90-degree angle. Then he's gonna go like in a linear trajectory in order to go and throw the dust that they got from the pool into another pocket. Also for the design, we decided to use the wheels, the blade wheels, in order to get better traction. And this is basically like the body right here. And now we have the conclusion.
So in conclusion, we kinematically analyzed 3-revolute robot. Initially, we did a path analysis which was parabolic, which yielded imaginary results. We quickly fixed this issue by simply changing the path to an elliptical one, which yielded more feasible results, more practical results. Also, in the dumping process, we chose a vertical path to be the most optimal path. Throughout this course, we were taught a lot of theories, a lot of conceptual ideas to apply in the real world, and through this project, we learned that all the theories we learned in class, we could easily apply them in the real world and in society. Thank you.